I'll introduce you and then I'll give you the floor. So, hi everyone. I'm very happy that today we can welcome XinRan Liu, who's currently in Edinburgh. He's an expert in low background screening methods, and he was working for a long time on Super NEMO and the LZ experiments, so rare event searches. He's also really done a lot of work on outreach and won in 2021 the IOP Mary Somerville Medal, which is the UK Institute of Physics for context. He's also an STFC Leadership Fellow in Public Engagement. But last year he decided to take his expertise elsewhere, and he's now head of research and innovation at Undo, and he will talk about his new adventures there today. Thanks.
Thank you so much for that excellent introduction, basically covering my first 3 slides. So perfect, even more time for questions. And yeah, thank you all for joining remotely, and good afternoon, good morning here, and good day generally. And thank you so much for the seminar organizers for inviting me to give this talk about my transition into a new field of dark matter. But yeah, so as Teresa mentioned, I previously worked for over a decade in neutrino and dark matter physics. Here in the UK, Bowlby Underground Laboratory, out in the US in the Sanford Underground Research Facility. I did my PhD at UCL in the Millard Space Science Lab, and I was an STFC Leadership Fellow, which kind of combines cutting edge research, which in my case was on LZ, so Lux Zeppelin dark matter direct detection, dark matter detector construction. But most of my expertise did focus on material assay, developing new assay technologies to push the sensitivity to radiation levels to ever lower levels, and also kind of increasing the throughput capability globally of sample assays for next generation of dark matter and neutrino detectors, such as Darwin, XLZD, or Legend. And but as part of the leadership fellow, it did buy out 40% of my time to focus on public engagement, building a community of public engagement here in the University of Edinburgh, Scotland, linking with other Scottish universities which have a physics focus, such as University of Glasgow, St Andrews, Aberdeen, Dundee, and Strathclyde. So, but the flagship experiment, the flagship experiment / flagship project that I led there was on something called Remote Cubed, which targeted schools in extremely rural and remote environments. So without easy access to university engagement days, science museums, and science open days, science festivals. So really bring the science to these regions and these schools. So we worked with 11 to 14-year-olds. We provided them with essentially equipment they needed to build a miniature Mars rover. And the reason for that is we have a Mars analog site used by NASA and ESA at the Bowlby Underground Laboratory, and they use the Mars yard 2 weeks a year, and the rest of the time it's kind of left empty. So we kind of, I came up with this idea for Remote Cube to kind of use and take advantage of that facility. And here you can see after 16 weeks, this is one of the robotic designs one of the schools came up with, and they essentially deploy in the Mars yard and try to complete as many tasks they can within a time limit as the Mars rover does the same challenges in the same location. And then afterward, they present it to their peers and families and school. And yeah, so that's been running for 2 years now, and still ongoing. And I still remain PI for that project, despite leaving much of my research responsibilities. And the reason for that is, as Teresa mentioned, in September last year, after the successful construction and operation and data taking of LZ, I decided to make a change and work in a whole new area of dark matter, but one that's definitely easy to find because it's readily available. But the science to quantify the measurements behind it still remains somewhat elusive. So forever working in developing new sensor technologies and measurements and material assay. And today, so I'm going to kind of talk about my move into the carbon dioxide removal space and talk about a new nature-based carbon removal solution called enhanced rock weathering, and then how we at Undo approach our measurement and reporting verification, and that's to quantify how much carbon dioxide is being removed and how much basalt is being weathered. And then I will cover about the co-benefits. So in a world where lots of technologies remove carbon dioxide, what sets us apart is the myriad of co-benefits that enhanced rock weathering provides, and then what impact that can potentially have globally. And I think, I just want to start by saying, the world of carbon offsetting, carbon avoidance, and, carbon dioxide removal can seem very chaotic, just looking at the news or reading papers. And it can seem kind of like a lot of smoke and mirrors. At least that was to me before I joined this field and had better understanding of how each of the different pieces of the puzzle all came together, and certainly it can then kind of put people off. And I recently came across a great article in an Australian newspaper about the Sydney man who's attempting to quit drinking, which I thought perfectly summarized the chaos of and some of the illusions around this area. So I think the man announced that he will quit drinking by 2050. Very good work. The Sydney man, Greg Taylor, has set this ambitious target. I really like this article, to phase out his alcohol consumption within the next 29 years. And as part of an impressive plan to improve his own health. So the program will see Greg, who's 73, to continue to drink as normal for the foreseeable future before reducing consumption in the year 2049 when he turns 101. But he has assured his friends that it will not affect his drinking plans in the short and medium term. Taylor said that it's important not to rush the switch to non-alcoholic beverages, as it's not realistic to transition to zero alcohol overnight. And this requires a steady and phased approach where nothing changes for at least 2 decades, adding that he may need to make some additional investments in beer consumption in the short term to make sure no nights are worse off. And Taylor's also be able to bring forward some drinking credits earned from days where he hasn't been drinking over the past 40 years, meaning the actual end date for his alcohol consumption may actually be 2060. So, this is often the kind of various complicated policies and behind the scenes move that kind of makes the field open to certain potential backdafters. And I think my aim today is to kind of convince you that what Undo does is trying to generate solid carbon dioxide removal and not, kind of selling any snake oil in that respect. But what's the scientific motivation behind all of this? While I think the climate change is widespread, rapid, intensifying, and unequivocally as a result of human-induced greenhouse gas emissions. And this was published by the IPCC in 2021, and the first time conclusively putting the cause of climate change directly as a result of human induced emissions. And then the follow-up report, which came out in 2022, states that all life on Earth, from ecosystems to human civilizations, is vulnerable to a rapidly changing climate. Follow-up report continues the theme, the deployment of carbon, but it specifically highlights that the deployment of carbon dioxide removal to counterbalance hard to abate residual emissions is unavoidable to achieve net zero goals. And there is a rapidly closing window of opportunity to secure a livable and sustainable future for all. So this is the latest report, which came out just a few weeks ago. And I think all of that summarizes the fact that we are facing a climate crisis, a near existential crisis for our species and many species around the world. And there is a real need to remove tens of billions of tons of carbon dioxide every year by the year 2050 in order to stay within sustainability goals and achieve net zero by 2050. Reducing emissions alone is still key, but we need to radically come up with new technology and undo some of the damage that we have done in the past. And that is where I guess the name undo comes from. Everything we do is designed to maximize the amount of carbon dioxide we can take out of the atmosphere and optimize the positive impact on the environment. So we do so using a nature-based solution called enhanced weathering. And before I talk about what enhanced weathering is, I will just briefly go over about natural weathering. So this is Earth's natural carbon dioxide removal mechanism, part of the long carbon cycle, just so that everybody is aware. So when rain falls to Earth, as it passes through the atmosphere, carbon dioxide in the atmosphere dissolves into the rainwater, forming carbonic acid, which falls onto land. And when it strikes mineral-rich rocks such as basalt, it reacts with the minerals such as potassium, sodium, magnesium in the rock, and then that breaks down the rock, forming bicarbonates, and that bicarbonate is then washed out into river systems and ultimately is transported to the ocean, where it then sinks to the bottom of the ocean and stored for geological time, which is tens to hundreds of thousands of years. So what we are trying to utilize and accelerate this natural regulatory system to draw down carbon dioxide faster and more efficiently. So how do you speed up this process? Well, there's a couple of ways. You can select very fast reacting rocks, and there's various rocks out there that can weather and capture carbon dioxide, but not all rocks are the same. We specifically select basalt due to its readily abundancy around the world, and also its very low levels of potentially toxic elements such as chromium and nickel, because the first and foremost our goals are not to contaminate the land that we operate on. There are other rocks out there, for example, olivine, which is very fast weathering, captures carbon dioxide much faster than basalt even, but there is an unfortunate direct connection between fast weathering olivine and the level of potentially toxic elements that's contained within it. And there are other rocks, for example, wollastonite, which also weathers fast, but it doesn't have nearly as much co-benefits as basalt. So due to all the various pros and cons, we have decided that basalt is the most optimum rock to operate with. And the next thing you do so the enhanced part of enhanced weathering is essentially just increasing the reactive surface area by reducing the particulate size. So we are using crushed rock, and by powderizing it. So I always give that example of, if you're trying to make your morning coffee and you chuck just beans into your cafetiere, you're not going to get a very strong brew, and you're going to be waiting a long time. But if you finally grind up the beans, you massively increase the reactive surface area, and then you can extract a very potent brew out very quickly, like the one I have here, and then start your day off nice and on a caffeine high, I guess. Yeah, so by taking crushed rock, we increase our reactive surface area and thereby speed up that natural process by 5 or 6 orders of magnitude. But crushing is energy intensive. But I always describe enhanced rock weathering as this 3 triple win scenario, because we don't actually have to do any additional crushing of the rock, because there is already an extensive aggregate industry that quarries basalt and crushes it for use in building roads and buildings. And what the particulate size they have no use for is the sub 4 millimeter size. So they're kind of left in. So this is an example of what basalt looks like. Giant Causeway in Ireland, very famous basalt deposit. And this is just a quarry, just so people have an idea of what it looks like to quarry basalt. And when here is a mound of basalt, which you can see that, yeah. So the industry has no use for these, and they're just left in huge stockpiles. So we simply take that byproduct and we use existing roads, infrastructure, and existing farm equipment. So this is a commercial lime spreader that farmers use to spread lime on their fields, and we just use the existing infrastructure to spread the basalt at 20 tons per hectare. So that's 2 kilos per square meter on the field, And once the basalt spread and once it rains, the weathering process will take place, and carbon dioxide will be transformed into carbonic acid and then bicarbonates. And then finally, ultimately, the resting place for that is out in the ocean. So this process, as we're not doing any crushing of the basalt, is and there's no additional processing, is 95% efficient, which means that our own carbon footprint for haulage and spreading the basalt only account for less than 5% of the total carbon dioxide that we're removing from the atmosphere. And that's part of Ondu's vision to keep the planet fit for future generations, with a mission to permanently remove over 1 billion tons of CO2 per year and help to deliver a sustainable and impactful solution towards carbon dioxide removal. So we are currently about 60 people at Ondu, and we operate locally here in Scotland, UK, but also globally, expanding globally. We have operations in the US and also looking to operate in Australia and other regions of the world. And we are built to scale. So the idea is to be the first company to remove 1 billion tons of carbon dioxide by the year 2030. And the reason for that very ambitious goal is because the very scalable nature of basalt, because it's so readily available, and agricultural land, which is, again, very readily available. And all of that ambitious goal is so that we have a chance to meet the Paris Climate Agreement goals of keeping the temperatures below the 1.5 degrees or 2 degrees limit. And simply because if we don't do so, the consequences could be catastrophic, with global crop failure, mass extinction, and Earth uninhabitable, which all sounds rather unpleasant. So achieving the Paris climate goal and staying within the 1.5 degrees Celsius above pre-industrial levels by the year 2100 requires rapid decarbonization. And if all the countries only meet their current nationally determined contributions for 2030, it's likely, with high confidence, according to the IPCC, that warming will exceed the 1.5 degrees Celsius during the 21st century. And there is a large gap between 2030 commitments and the magnitude of emission reduction needed to limit warming to less than 1.5 degrees. And stabilizing global average temperatures will require reducing CO2 emissions to net zero. So these are just some of those facts. And I don't want to give the illusion that carbon dioxide removal is the solution to all of our problems, because we really need to rapidly reduce our current emissions. This is first and foremost and the most impactful thing we can do. We are currently emitting something like nearly 60 billion tons of CO2 per year. And what really needs to happen is through transitioning to renewable power, renewable waste for heating homes, and building up extra capacity in wind and solar and other renewable energies, and building more energy efficient buildings, improving public transport systems, and various other pathways to reduce emission. The IPCC states that we really need to cut our emissions by 80%. And that is obviously the most impactful effect we can have on limiting global climate change. But I'm not going to talk about any of that today. I'm actually going to talk about the remaining 20% emission from industries that will be very hard to decarbonize, which we need to match in terms of carbon dioxide capture, storage, and removal. So there we need new technology to counterbalance the remaining 10 to 17 gigatons of carbon dioxide per year that we need to remove in order to reach net zero. So yeah, in the world of carbon dioxide removal, in the remaining 20% current technologies to meet that remaining 20% requirement and demand, not all of them are the same. And I kind of try to summarize them in this table of various solutions, technologies, and they broadly are about 6 different techs: enhanced rock weathering, biochar, which biochar is where it's a carbon storage technique where when trees die, so that's why afforestation is a low permanence technology, because when you plant forest they rapidly capture carbon, but when the tree dies, most of that carbon is then re-released. But you can biochar your tree in a high furnace and then kind of lock that carbon away in the form of biochar. Direct air capture. So this is kind of pumping CO2 from the air into the ground. There's also bioenergy, carbon capture and storage, BECCS, and then also soil carbon, so through soil organic carbon. So you can see that here, I've kind of tried to summarize them in difference of high permanence. So this is kind of tens to hundreds of thousands of years of storage, whereas low permanence is really decades of storage. Deployment speed, how quickly this can be deployed and scale up. And then whether or not it competes for existing land use, which is very critical, because I believe to meet the UK's net zero goals, we would have to cover a large proportion of the UK in forest, and that would be obviously not practical for existing farming industries, and the cost of the technology. So ultimately, that also relates to the cost of carbon per ton removed. So the higher end for direct air capture is order of thousands of dollars per ton, and the very cheap end for carbon dioxide, I think you can. There are certain things on the market for for some tree credits that are of order, $5 to $20 per ton, but then there are definitely issues associated with those authenticity of those credits. And then, of course, as I mentioned earlier, the co-benefits. So in a world where everything is removing carbon dioxide, which have other benefits to the environment. So I think I just kind of try to use this table to summarize that enhanced rock weathering performs very well across the board. Obviously, I kind of selected the categories, but I think these are 5 very important categories to me when judging for carbon dioxide removal technology. And certainly what I was looking for when I left particle physics, high energy physics, looking out there at the various technologies and which area I want to move into, enhanced rock weathering really stood out as a very scalable technology to meet the kind of rapidly increasing carbon dioxide removal demands globally. So how do we at Undu aim to verify our carbon dioxide removal and make sure that the basalt is weathering in the fields and CO2 is being taken out of the atmosphere? And our vision is to do so using a combination of a geochemistry model with in-field measurements, whilst developing new technology to advance the science in order to create a gigaton scale removal pathway. So MRV is measurement, reporting, verification, which really stands for kind of verifying your weathering taking place and carbon dioxide being removed. So CDR is carbon dioxide removal. I'm trying to avoid using any jargons. And the reason to use this model measure approach, we feel, is because to date, there is no single method that has proven to be accurate in quantifying the amount of carbon dioxide being sequestered, but rather there are lots of proxy parameters that can be measured. So indirect measurements of, so I think for people who work in dark matter physics, they will appreciate direct and indirect measurements. Lots of indirect proxies that kind of show you weathering is taking place. And that's why we use our model measure approach. And what sets us apart is we really try to measure all of the weathering proxies in order to build a complete picture and see the full picture of weathering from various different proxy signals, and use that to accurately quantify how much carbon dioxide has been removed. So we, in terms of our geochemical model, we are using an extensively peer-reviewed one-dimensional reactive transport model. This was developed at the University of Sheffield as part of the Leverhulme Center for Climate Mitigation, led by Dr. Peter Wade, supported and led by David Bierling, who is a world-leading figure in the world of enhanced weathering, and then supported by Amy Lewis, Mike Helen, and others. And Peter and Amy and Mike are now working as part of the Undu science team. So we are continually improving this peer-reviewed published model and adding proprietary additions to make it more closer to real-world situations and scenarios, especially in the areas and regions of interest that we operate in, and adding in new information and conducting new experiments where there is missing or where some information might be outdated, trying to do our own experimentations to update certain parameters within the model. And we're also using real-world published data of enhanced weathering results out there to calibrate and continually improve that model. And whilst waiting for our own trial data to further, ground truth the model. And this is not a real result. This is just kind of to show that the model simulation would give you an estimated carbon sequestration over multiple decades. And then ideally our field trials would produce results of weathering parameters that it estimates broadly matching that kind of that trend over time. And the geochemical model so far, it's incredibly complex, but broadly takes into account 4 main categories of input variables. And those are kind of basalt, climate, soil, atmosphere. So we like to fully understand our basalt from cradle to grave or from quarry to ocean. And so every single quarry we operate out of, we measure the basalt extensively for the mineralogy. So we fully understand the content of the rock, and therefore allows us to estimate its weathering potential. We also check for the reactive surface area, and also we check for the potential toxic element levels in the basalt. So because first and foremost, we do not want to contaminate agricultural land. And we do so every 3,000 tons. So if a quarry is selected for deployment on land, we check the rock every 3,000 tons of operation to ensure the mineralogy remains consistent, and more critically, the potential toxic element remains below safety limits. Actually, there are no current regulations in the UK relating to safety limits, but we have found the most stringent limit out there and kind of abide by those, and those are some EU limits set by the European Union for soil amendments. We also take into climate data. By far, the biggest driving force behind enhanced weathering, as you can imagine, is rainfall, because rain is the ultimate carrier of the carbon dioxide to the rock, and temperature. So chemical reactions, higher temperatures, faster reactions. Soil, every single farm we spread on, we take baseline samples to understand our soil pH, texture, and various other parameters that goes into the modeling, and also atmospheric CO2 and soil CO2 partial pressure. So a lot of things goes into the model. And then all of those enable us to generate a carbon sequestration curve over multiple decades. And the reason for taking to those parameters is because not all basalts are the same, and not all locations are the same. And the reason, for example, using the same soil and climatic conditions, carbon dioxide removal potential of different basalts we found can vary by up to as much as 6.5 times between various basalts. And also your reactive surface area can also have an impact to your weathering rate by a factor of 2 or 3, so 2.8. So not all basalts, that's why it's important to check the basalt. And also we have global data sets as well to enable us to work out heat maps of various countries we operate in, the optimum weathering locations based on rainfall and temperatures and all the other parameters. Once you have those data, calculating carbon dioxide removal comes in 3 steps, I guess. So we model we model the basalt. So earlier, so this is one specific basalt quarry that we have here in the UK, and we have sampled this rock and found there 5 primary rock phases: algae, andesite, and various other materials in there, and you can see that over time, so this is over a 50-year period, each of those, so andesite weathers very fast, as you can see here in blue. It weathers away and is nearly fully weathered after 25 years, whereas glass doesn't weather very much at all over time. So by knowing each of these rock phases and how quickly they weather, we then do a charge balance calculation, because in the world of chemistry, everything must be charge balanced, to kind of calculate the amount of concentration of bicarbonate produced. And from the bicarbonate production, we can then also estimate carbon sequestration. So then by combining all these 5 different weathering rock phases, you have a single carbon dioxide sequestration curve over time. So this is over the 50-year period. You can see that, yeah, so for 20 tons per hectare, for this rock specifically at this location we modeled it for, it would sequester just over 5 tons of CO2. So that's a 4-to-1 ratio of carbon dioxide. So for every 4 tons of rock, we expect 1 ton of carbon dioxide removal. But of course, there's lots of uncertainties around those input parameters. So we run Monte Carlo simulations, taking the mean of each of those input parameters, but also the uncertainty associated with each. And we run large Monte Carlo simulations to kind of see what is the uncertainty band over the 50-year period. So we get this heat map where you have the carbon sequestration curve, which is the mean, but also the ±2 sigma uncertainty of where your carbon sequestration might sit over that 50-year period. Yes, but I think largely a lot of those uncertainty reduced to become very small after the 50-year period, simply because, as you saw earlier, when certain rock phases like Andesine is fully weathered, the uncertainty associated with those then reduces to very low, and therefore I think our most uncertain phase sits at around about 16 years. And then the uncertainty at 50 years is really plus or minus 2% around the mean. So in terms of measurement, then to kind of check and sanity check the model, we are trying to, as I mentioned earlier, deploy all the existing cutting edge technology to measure weathering signals, but also combining that with more traditional soil sampling approaches to measure parameters that show us the weathering taking place. And those are, for example, as the chemical reaction for enhanced weathering takes place, there is a change in soil pH. That is actually one of the major co-benefits, which I'll talk about later. But also, there's release of cations such as calcium, magnesium, sodium, potassium. So we check for pH changes, total alkalinity in our pore water. Also, we check for cations in the pore water. And we also try to measure the basalt directly using isotope approaches to see the weathering of the basalt having taken place. And of course, we also check for crop yield, and also we digest some of the crop to check for uptake or changes in potential toxic elements in the crop. And yield response is a weathering indicator in this case as well. And we kind of measure all of those. So we use those data. And we use we compare those to model outputs to triangulate weathering rates. So our field experiments really come in 2 different forms, using 4 different measurement techniques. So we have field trials, which are on the bottom right here, and also mesocosm experiments. So we use mesocosm experiments because they incorporate a lot. So mesocosms are a cool industry word for essentially a soil column. So this is essentially a 20 centimeter diameter pipe that has extracted a 30 centimeter deep soil core from the ground, and it's being instrumented with these rhizome samplers, which are essentially syringes that can have a vacuum applied to them and draw pore water out at different depth. And the reason for that is, and then also one of the advantages of mesocosms is also the ability to collect the leachate, so the water that's kind of fully gone through the soil cores, and then we can collect at the bottom, which you don't have the luxury to do in field, or not easily. We are designing an experiment to do so in a larger field trial. But yeah, so we use mesocosms because they incorporate much of the complexity of field conditions, especially if you leave them in the field. So this is a beautiful picture taken here in Stirling, Scotland, of when our mesocosms were established in freezing conditions. And then they sit right next to the field trials that take place right beside them in the same location. So try to capture as much of that weathering condition as possible. But you can have much higher control. And one of those really interesting things is to control the basalt application. So whereas you're using commercial spreaders to spread at 20 tons per hectare, that kind of averages out to be 20 tons per 2 kilos per square meter, with an average particulate size of what you measured. But for any specific patch where you instrument, that might not be quite the case. Whereas with the mesocosms, you can very finely control and make sure the basalt is applied in as uniformly and across the cores, and also within each core to what you measured from the quarry. And therefore, it provides you a very controlled experiment to use the data to further improve, calibrate your geochemical model. Our field trials aims to do same, but in real world conditions. So we have in situ sensors, where these sensors on in the middle here are pH EC sensors to show us real-time live changes in soil pH control versus basalt applied plots. And we also take soil samples frequently, pore water. So again, these field trials also have those rhizome samplers to extract soil pore water at various depths, and that's done every 2 weeks. And finally, we digest the crop that's grown on top to check for the uptake of cations. I will go through this very quickly, but just to show that we take lots of measurements and we use lots of analysis techniques to kind of allow us to triangulate how much weathering is taking place in order to accurately quantify basalt has weathered, and therefore how much carbon dioxide is being removed. And then I'm just going to move on to the co-benefits very quickly. So for every ton of carbon removed, there is a range of co-benefits, and the main one is the soil pH change. So that's also a parameter that we track to quantify weathering. And the reason for that is because if here in Scotland and most farms, depending on where you are, what the bedrock you sit on is, the soil will tend to move to more higher acidity over time. So farmers here in Scotland will have to lime their soil every 2 to 5 years to bring that pH up. And the reason is because if the pH falls too low to the region of 5, a pH of 5, then even if there's lots of nutrients in the soil, even if you apply fertilizer, the plant is not able to access those nutrients and they're locked away. So by bringing the pH up, you can better use the existing nutrients in the soil and use them more efficiently. So that's why farmers apply lime, but the weathering process. But the problem with liming is that when you lime, it very quickly increases your soil pH, and then it kind of tails off, and then every 2-5 years, and then you have to reapply, and you have this like large wave effect. Whereas with the slow weathering process, a slow release, as we showed earlier, over the 20-50 year period, there could be a scenario where you can maintain an optimum pH level with minimum reapplications over time to kind of keep your pH at a stable, say 6.5. Depending on what crop you're growing, what kind of land, what you're using it for, there's different optimum pH levels. But whatever the farmer might choose, you can kind of, we're moving to a phase where we can produce a tailored approach to kind of maintain that pH level, which is a major benefit. And of course, beyond just making the soil higher pH, making the nutrients more available, here on the top right is also a table summarizing one quarry of kind of typically the nutrient content of basalt. So lots of macro, micro, major nutrients that's being released into the soil over time as well. So there is a cost-saving element for the farmers, as they will have less reliance on liming, less reliance on fertilizers, and those are expensive and also carbon footprint intensive to lime and to apply fertilizer. And then also there are certain indicators such as calcium, silicate weathering releases silicates, which are taken up by the plant, strengthening cell walls, making them more pest resilient. But also, we're currently conducting studies with Newcastle universities and other partners here in the UK to check for the increase in soil microbial activity and overall improvements to soil health, as well as potential improvements to soil organic carbon content as well. So lots of co-benefits as a result of basalt weathering. We are currently running 12 trials here in the UK across major crop types, and also 5 trials in the US, Pacific Northwest and Washington, covering again the major crop types. And we do so in every region we operate out of, just fully understanding our model, how the model performs at every new region of interest. And that's defined very much by climate zones, because climate is the biggest driving factor for weathering. And there is a well-established global map of climate zones. So in new regions for Pacific Northwest, very different climate to Scotland, we established field trials to in order to take measurements to further demonstrate that our model is working robustly in these different weather climate zones. Yeah, so lots of more data to come. We also have our own data working with Newcastle University and their research farm, which kind of demonstrates the impact of 1 year application of basalt 20 tons per hectare. But that is due to be submitted for publication next Monday. So we're not currently sharing the results, but it demonstrates the co-benefits of basalt in terms of crop yield and also changes to soil health, which will be available shortly. Yeah, and all of this is to say that, I think I want to highlight that this is a very scalable operation. There's lots of quarries here in the UK, but importantly, there's lots of quarries globally. These are just some that we've identified, and we're scaling up at this factor 10 increase basis. So last year we spread 30,000 tons of basalt, and this year we're aiming to deliver nearly 200,000 tons of basalt on the ground, and scaling up rapidly, and just kind of demonstrating what impact that could potentially have. So in the UK, using existing arable croplands and existing quarry byproducts, there is an estimated, there's publications that estimate the carbon dioxide removal potential for basalt to sit around about 6 to 30 megatons of carbon dioxide per year by the year 2050, and that has the potential to account for 45% of the removal requirements of UK government's net zero emission targets. So potentially a major contribution to the fight against climate change, but by all means not the only solution. So I think in the CDR space, as with emission reduction, we really need to do everything everywhere all at once, to quote a famous Oscar-winning movie. And so this is just one very powerful tool, but there are definitely room for others as well. And just to kind of demonstrate the global impact, there's lots of arable land globally, and also there's lots of basalt globally. So that is why it's such an optimal material to work with, because it's so readily available across the world. And also, just to give a demonstration of what does a megaton look like, I kind of at 20 tons per hectare, it's really a circle with a 25-kilometer radius. So as talking to the University of Sydney today, and having been to Sydney and traveled through Australia, beautiful country, and I'm particularly a fan of the Blue Mountain National Park. And so I put a circle around with a 25-kilometer radius around the Blue Mountain. So if we cover this area with basalt, it will improve any plant growing there in terms of health, but also that is sufficient to sequester 1 megaton of CO2. So that's kind of the kind of global scalable impact potential of this technology. I just want to finish by highlighting the incredible science team I have the privilege to work with and lead. And I think MRV is being a difficult challenge, verification is being a difficult challenge in the enhanced rock weathering community. So it's been incredible here on Liu to assemble this team of experts across lots of fields of science. So we have microbiologists, geochemical modelers, experimental geologists, Christina, who spent over a decade measuring greenhouse gas emissions in Greenland, agronomists, machine learning engineers, soil scientists, and then myself and Will, particle physicists. And it's been an absolute delight to bring these different expertise and tackle these complex problems coming from different areas. And it's been very complementary, and kind of it's been speeding up the process at which we can deliver a scalable MRV approach for global operations. So where we do have lacking in knowledge, we have also been building up international partners. So everywhere we operate, we work with local partners, and also, so we work with national labs in the UK, US, universities in the UK, US, Africa, Australia, and also industry partners here in the UK to develop new MRV approaches, but also to kind of study accurately the co-benefits of basalt and also any new technology that we can kind of bring to bear on our soil in order to create a scalable global measurement approach to ensure that our when we say carbon dioxide is being removed, it is indeed the basalt is indeed being weathered, and the CO2 is being taken out of the atmosphere and not re-released. Thank you very much. Happy to take questions.
All right. Thank you very much for your talk. Does anyone have questions? Feel free to just, yeah, Roland.
Thanks for the terrific talk. I had a heap of questions, but I mean, I guess maybe the main one is, what is setting the ultimate limit on this idea? I mean, why not just scale it up so it's bigger than current CO2 emissions, and everything's the whole climate crisis is solved immediately, right? So what is setting the ultimate limit on how effective this process can ever be?
Oh, I see. So you mean just kind of instead of doing the 80% emission reductions, we just ramp up enhanced weathering by factor 5.
Yeah.
So the limitation is, so first of all, the 95% efficiency is estimated on taking this industry byproduct. And there's estimated to be about 600 million tons of waste product generated by quarries annually. So, with a 4:1 ratio, that would account for about 150 million tons of CO2 removal. To move beyond the megaton scale to gigaton, we would probably need to move into a model where additional crushing processing would have to be done specifically for basalt application. But we have also done a life cycle analysis of that process, and using current technology, current quarrying capabilities, that still sits at something like 88% efficient. So higher carbon footprint of the additional processing of basalt, but it's still a very viable approach. And you can definitely imagine a scenario where, here in Scotland, we produce excessive amounts and literally of wind power. And there are times when there's more power than can be uploaded to the national grid, and it's kind of being wasted. And you can imagine a scenario where you have basalt grinding facilities which only do the crushing at times of high power. You're using the excess power, no additionality of power needed, right? So you can definitely make that a more efficient process. And then also there is readily available huge amounts of agricultural land, but currently we only spread within a 20-mile radius of our quarries. I don't think I said that earlier, actually. So we are limiting ourselves to that small radius. Our life cycle analysis was done on a 50-mile radius estimate. But so right now we're kind of, I mean, there is possibility you can scale this thing. There are the aggregate industry that quarry basalt today operates in the a multi-gigaton scale. So there is that much rock available out there. But yeah, I think reductions are still, I mean, I think we probably over emit, and there is definitely room for reductions there. But there is also definitely potential to scale this technology up. The major barriers are, so going beyond using just byproduct, doing your own crushing, and then I guess, and then kind of applying to agricultural land. But once you have that supply chain set up, we haven't internally, I think, worked out what is the kind of, with all the existing land around our quarries within 20-mile radius, what is the total potential of that? But I think that's something we can do internally.
Cool, thank you.
Great. I've got a question as well. You mentioned kind of that it depends on the climate as well, how efficient it is. Do you already kind of have ideas of, is a colder climate in general better? Is a warmer climate better? Do you have any indications there already?
Yeah, for sure. I mean, I think the tropics is an ideal area to apply basalt application. So places like Brazil, but then there are other complications, for example, because I think historically Brazil has always used, and actually here in the UK too, apparently I found out talking to some farmers that in these pumpkin growing competitions, basalt rock has been a well-known secret of trying to make your pumpkin slightly larger. Even hundreds of years ago, people have been applying volcanic rock. And actually, I was recently watching a David Attenborough documentary, and you have these volcanic these civilizations that live near active volcanoes because they have very fertile soil, right? It's the same process. The volcanoes erupt, they release huge amounts of essentially volcanic rock that weathers to produce very fertile soil. So every so often your civilizations rise and fall. But we have internally generated global heat maps of weathering potential to find the most optimum weathering zones. But essentially, you want somewhere with lots of rain and very warm. Scotland has lots of rain, but it's not so warm. And then yes. So you can limit yourself to operating in just very optimum conditions. But then that band broadly sits, around the equator. But yeah, I mean, I think, but the problem with operating in places like Brazil, which is very hot and rains a lot, is they have a history of adding basalt to their land already, and then there is an additionality problem of you have to do something new and not already done in order to generate carbon dioxide removal credits. And if people are already applying this, I don't think you can retrospectively go back and ask for carbon dioxide removal credits as a result. If it's already a standard practice of farming in that region and you're not doing anything new, then you're not in essence removing any additional carbon dioxide. So that's very much the claiming beers for days you didn't drink scenario, which would be bad.
Thanks. I think Roland has another question.
Well, yeah, if nobody else is going to ask any questions, I had a couple more questions. So one of them you started to answer, which was I wanted to understand what the financial model was. I mean, is the farmer paying, or is the company getting carbon credits, or how is the whole thing financed? And the second kind of naive question was, what happens if you dump this this finely crushed basalt into the sea? Does that also work?
Yeah, there is a large sector of industry and academic studying of rock weathering in ocean, but that's a totally different. I mean, you can do that, but there's a lot more things to study there. To me, in terms of doing measurement verification, your rock, doing quantifying weathering in the ocean as your rock sinks, or if you can try to suspend it, is even more difficult than land. Because even on land, it's an open system, but in the ocean, infinitely more complex. And also dumping gigatons of basalt in ocean, and the effect of that on local ecosystems is hard to quantify, and it probably need more study as well. But it's definitely an area people are actively looking into, and lots of research publications are around. In terms of financing, yeah, so we currently buy the rocks from quarries. So we buy this byproduct from quarries, and we pay for the haulage and spreading it on farmland, and we give it to farmers for free. And how we generate the profit is we sell verified carbon removal credits on the voluntary carbon market. So, like, for example, recently we formed a partnership with Microsoft, and they have agreed to, for example, buy a certain amount of carbon credits for the delivery of 5,000 tons of basalt. No, 20,000.
Yeah, thanks.
Cool.
You kind of mentioned earlier already that, if you already spread the basalt on like an area, you can't just do it again. What would be kind of be the life cycle be when maybe the basalt has captured everything it's gonna capture, and you would use that area again and add more to it?
Yeah, so I should be I think we can reapply, and we're currently internally looking at this reapplication on the same land year on year. So there are trials in the US at the University of Illinois which apply 50 tons per hectare year on year. So the basalt now is sitting at 200 tons per hectare, and they have seen year on year yield of 12 to 16% increases as with our basalt application, and no additionality of potentially toxic elements. So you can reapply, and they apply that's a very extreme reapplication. We apply at 20 tons per hectare, and what we're aiming to do internally is trying to find, as I mentioned earlier, like a tailored reapplication rate for a farmer to say, if he comes to us and say, I really like my pH at this 6.5, and then we would go and take baseline samples of his soil, study the uniformity of his farm. If he has 1,000 hectares, that's not going to be all the same, and then work out a tailored application and reapplication rate to kind of keep that pH at a more constant level. But the only reason to avoid heavy application, I mean, I guess if you apply a lot of basalt, actually we've done trials where we apply 200 tons per hectare, and at first you do have this layer of basalt on top, right? But it takes about 6 months to be incorporated into the soil, and afterward it's okay. But for certain crop types, you might not want to apply such a thick layer of basalt. And also, not all basalts are the same, and there are regions where basalt does have higher levels of potential toxic elements than others, still below the EU safety limits. But we're also studying kind of what is the multi-year, if you apply 50 tons every year for say 20 years, what is the accumulation effect of chromium and nickel, and kind of, yeah, where that goes ultimately, I guess, as well. So we're taking a very cautious and conservative approach to start, and as we understand it better, we will consider like moving and ramping up.
All right, thanks. And are there any last questions? If not, thank you very much again